Okay, just today we're going to look at this idea of limits. Now, the idea of a limit is when you're investigating graphs at certain areas. There's different ways of approaching it. The easiest type is one you can just do by direct substitution. So you might have the function x plus 7, which obviously is a straight line. And you want to know what's happening as the x values are getting closer and closer to the value of 5. Well, something like this, you could just substitute straight in. You say, well, if it was getting closer to 5, then on the line x plus 7, then the function value must be getting close to 12. So straight substitution, of course, would be the easiest way of doing something. Doesn't always work, however. This sort of graph, x squared minus 9 on x minus 3 as x approaches 3. Now, if we were to draw it, we'd end up with a point discontinuity at x equals 3. X equals 3 doesn't actually exist on this particular function because bottom of the fraction can't equal 0. So if we were to investigate, straight substitution is not going to help here because yes, I get 0 on the bottom of the fraction, but I also get 0 on the top of the fraction as well. And so there's that never-ending question, what is 0 over 0? Some people say it's 1. Because you've got the same thing on the top and bottom, so it must be 1. Some people say it's 0, because you've got 0 on the top of the fraction, and that always gives you 0. And some people say, well, it's undefined, because you've got 0 on the bottom of the fraction. Well, undefined, it ends up being the correct answer, because we can't have several different answers for the same thing. So something like this, we try and factorise, and fortunately in this one it does nicely. Top of the fraction is different to 2 squares. The x minus 3's cancel, and we can say, all right then, well, I know that 3, it doesn't exist at that point, but if I substitute into x plus 3, it would be getting closer and closer to a function value of 6. Okay? So we can't actually have that point, 3, 6, but it would be getting closer and closer to a value of 6 as your x value is getting closer and closer to a value of 3. Now, this special limit which helps us investigate. As x approaches infinity of 1 on x equals 0, and I guess the easiest way of explaining this limit is to think of our hyperbola, the actual graph of 1 on x. And as those x values are getting bigger and bigger and bigger, well, the function itself is getting closer and closer and closer to 0. Now, of course, we can't physically substitute in infinity, and so this is where limits really does come in handy. So I get something like this. If I want to substitute in infinity, well, imagine if we could. Infinity cubed, well, that'd be quite large, plus 3 times infinity squared, well, that's even bigger now, plus 2 times infinity, now it's really big, minus 1, so what? But then we're going to divide it by 4 times infinity cubed, again really big, minus 1, well, again when we're talking about infinity, subtracting 1 is sort of insignificant. So we've got this really, really big number divided by this really, really big number that we don't know what it is because you can't substitute in infinity. How do we deal with it? Well, the only thing I know for sure is that the limit as x approaches infinity of 1 on x is equal to 0. So what I try to do is rewrite every term so that the only place I see the pronumeral x is in the bottom of the fraction. And to do that, I divide everything by whatever the highest power is. So I'm going to divide everything by x cubed. Then each of those individual terms can be rewritten where x is only in the bottom of the fraction. And now I can, if you like, substitute in infinity because we know that the limit as x approaches infinity of each one of those fractions would be 0. And so I'm just left with a quarter. Now, if you look at it very closely, we can save ourselves a bit of time. Because what we've essentially ended up with is the coefficients of that biggest power. And that's always got to happen when you think about it, because if I'm going to divide by the highest power, well then, in this case x cubed, all the x cubes are going to cancel out, whereas all the other ones will be left with x on the bottom. So I get something like this then. Again, x cubed is the biggest power, but all I really need to say to myself is, well, I know I'll be left with the coefficients of the biggest power. Now on the top of the fraction, that would be 0, because there are no x cubes on the top. On the bottom it's 1, well 0 over 1 equals 0. So this particular graph, whatever it looks like, but at an infinity, it must be getting closer and closer to the x-axis, getting closer and closer to 0. So again, you could look at one like this. I can chuck in 974 there just to make it look whoa. But it's irrelevant, because we're dealing with such a large number, infinity. We're only interested in the x to the 7s, really. And so we'll end up with a third. So that particular graph will be going towards a function value of a third. X cubed's the biggest again on this one. So this time I end up with 1 on 0, which is undefined. But what it means as far as our function values are going, they must be approaching infinity. We're getting closer and closer to that undefined result. Now, we often make the mistake of saying 1 divided by 0 is infinity. That's not true. 1 divided by 0 is undefined. But the limit, and that goes back to our special limit, as it approaches infinity, 1 on x would equal 0. So 1 on 0 is undefined. But when we're talking about a limit, we know, okay, it's going towards infinity. So back to this sort of question, when we were doing our graphs before, and we had to find horizontal asymptotes, things like that, it gives us another way of finding those. Because I'm saying, well, horizontal asymptotes, you remember, is what happens out at infinity. So I'm saying, well, what's the limit as x is getting bigger and bigger and bigger? And if I was to expand that out, I've got x squared plus x minus 6 on x squared minus 1. So now I can just look at that and say, oh, well, that must be going towards 1. So I know I've got a horizontal asymptote of 1. That's a little bit quicker than doing all the polynomial division and all that. Our textbook doesn't have an exercise on limits. I never understand this, because the next thing we're going to do tomorrow is look at differentiating from what's called first principles. And we need to handle limits in that. And I never understand why we don't have something on limits. So from a different textbook, the old Terry Lee textbook, exercise 6.1's just a handful there to have a go at, to get a bit familiar with how we find limits and what have you.